What if everything you think you know about the beginning of the universe is just the tip of an iceberg so vast, so bizarre, it defies comprehension? Picture this. The cosmos didn't just burst into existence with a polite explosion and call it a day. No, the opening moments of our universe were more like the wild, untamed first seconds of a blockbuster movie, full of plot twists, unanswered questions, and scenes so strange, even the smartest scientists struggle to explain them. And here's the thing, we're not talking about just one or two theories about how it all began. There are dozens, each more mind-bending than the last, from universes bubbling out of nothing to cosmic collisions we can't even fathom. Think about the Big Bang for a second. We've all heard of it the moment everything began, right? But what if that's just the simplified version, the abridged story we tell because the real one is too overwhelming? The truth is, the deeper we dig into those first fractions of a second, the weirder it gets. Some theories suggest the universe didn't even have a true beginning, just an endless cycle of rebirth. Others propose that our entire cosmos is just one tiny bubble in an infinite foam of universes, each with its own laws of physics. And then there are the ideas so out there, they sound like science fiction, like the possibility that time itself didn't exist until the universe decided to hit play. That's what we're diving into today. 30 of the most astonishing, awe-inspiring, and downright puzzling theories about how the universe kicked everything off. These aren't just wild guesses, they're the cutting-edge ideas born from the minds of physicists, cosmologists, and thinkers who stare into the void and dare to ask, what if? Some might turn out to be true, others might fade away as science marches forward. But one thing's for sure, by the time we're done, you'll never look at the night sky the same way again. So buckle up, because we're about to take a journey back to the very edge of existence, to a time when reality itself was still figuring out the rules. The Big Bang Theory isn't just the most famous explanation for how the universe began, it's the foundation of modern cosmology. Imagine squeezing everything that exists, every star, every galaxy, even the space between them, into a single point so infinitely dense and hot that the laws of physics as we know them break down. That's the starting point of this story. Then, in an unimaginable flash, this singularity exploded outward, expanding faster than the speed of light in a process called inflation. Within the first few fractions of a second, the universe transformed from a seething, chaotic soup of energy into something more recognizable, particles forming, forces separating, and the stage being set for everything that would follow. But how do we know any of this actually happened? The evidence isn't just convincing, it's everywhere. Take the cosmic microwave background radiation, often called the afterglow of the Big Bang. This faint, uniform glow fills the entire universe, a cold whisper of that initial fiery expansion, now cooled to just a few degrees above absolute zero after nearly 14 billion years. Then there's Hubble's groundbreaking discovery. Galaxies aren't just drifting apart, they're racing away from each other, propelled by the universe's ongoing expansion like raisins in an ever-growing loaf of cosmic bread. Yet, even with all this proof, the Big Bang Theory leaves us with mind-bending questions. What came before it? What triggered that initial expansion? And perhaps most unsettling of all, what if the Big Bang wasn't the true beginning, but just another chapter in an even grander story? The deeper we look, the more mysteries we uncover, proving that even our most well-supported theories are just the starting point for a much bigger conversation. The Big Bang gave us the universe, but it left behind puzzles that kept scientists tossing and turning at night, until Alan Guthr's revolutionary idea of cosmic inflation untangled them in one brilliant stroke. Imagine the early universe not just expanding, but inflating faster than light itself, doubling in size over and over again in mere fractions of a second. This wasn't just rapid growth, it was a hyper-driven stretch that smoothed out the cosmos like ironing out wrinkles in a vast cosmic bedsheet, Without inflation, we'd be stuck with mysteries like why the universe looks so uniform in all directions, or how regions of space too far apart to ever interact somehow share the same temperature. Inflation answers these with elegance. The entire visible universe was once a tiny, ultra-connected speck before it ballooned to unimaginable scales. But here's where it gets even wilder. Quantum fluctuations, those tiny, random jumps in energy at the smallest scales, got stretched along with the universe during inflation, leaving behind faint fingerprints. These microscopic irregularities became the seeds for everything we see today. Picture a calm pond suddenly rippling with tiny waves. Those ripples eventually grew into the galaxies, clusters, and cosmic voids that define our universe's large-scale structure. Without those quantum hiccups, matter would have spread out too evenly, leaving nothing to clump together into stars or planets. Inflation didn't just solve old puzzles. It handed us a new story, one where the universe's biggest structures owe their existence to the tiniest flickers of quantum uncertainty. Yet inflation isn't a finished tale. Some versions suggest it never truly stops, birthing an endless web of pocket universes, each with its own unique physics. Others debate what triggered it in the first place. Was it a quantum accident or something deeper? What's certain is that Guth's theory reshaped cosmology, turning the Big Bang's aftermath from a confusing mess into a canvas where even the smallest quantum jitters could paint galaxies. What if the Big Bang wasn't a one-time event, but just the latest in an endless series of cosmic resets? The cyclic model dares to suggest exactly that, a universe with no true beginning or end, only an infinite loop of expansion and collapse. Picture a cosmic heartbeat where each thundering Big Bang is followed by a slow, crushing Big Crunch, collapsing everything back into a singularity before erupting outward once again. It's a vision of time as a circle rather than a straight line where every ending seeds a new beginning. This idea isn't just poetic, it's rooted in real physics. One of its most striking variations comes from Roger Penrose, a Nobel Prize-winning physicist who proposed something called conformal cyclic cosmology. Penrose's theory imagines a universe where the distant future, a cold, empty expanse where black holes have evaporated and particles have decayed somehow loops back to become the ultra-dense, high-energy conditions of a new Big Bang. The key, a mathematical trick called conformal rescaling, where the vast, stretched-out emptiness of the far future is effectively reset to a state indistinguishable from the primordial singularity. But here's where it gets truly mind-bending. Penrose claims to have found evidence of these past universes imprinted in the cosmic microwave background, what he calls Hawking points. These are faint, circular patterns in the afterglow of the Big Bang, which he interprets as the last whispers of black holes from a previous cosmic cycle. They're named after Stephen Hawking, who theorized that black holes might leak radiation over eons, leaving behind ghostly signatures. If Penrose is right, these points could be the first tangible clues that our universe is just one page in an infinite cosmic storybook. Of course, not everyone's convinced. Critics argue these patterns might just be statistical flukes, cosmic static masquerading as something deeper. But whether or not the cyclic model holds up, it challenges us to rethink time itself. Maybe there was no first moment, just an eternal rhythm of creation and destruction, where every ending is a prelude to a new explosion of existence. It's a humbling thought. Our entire universe might be nothing more than a single breath in the endless life of something far grander. String theory doesn't just rewrite the rules of the universe, it shatters them, suggesting a reality so vast and varied that our cosmos might be just one note in an infinite symphony. At its core, this framework proposes that the fundamental building blocks of reality aren't particles but tiny, vibrating strings, each oscillation dictating the properties of matter and energy. But here's the twist: these strings don't just dance in the three dimensions we know. they require at least 10 dimensions to make the math work, meaning there are hidden layers of space curled up so tightly we've yet to detect them. And within this labyrinth of extra dimensions, the theory predicts something extraordinary, a landscape of possible universes, each with its own unique physics. Picture a cosmic casino where the constants of nature, the strength of gravity, the mass of an electron are just random rolls of the dice. This is where the concept of branes comes in. Short for membranes, these aren't just abstract ideas, they're vast, multidimensional surfaces where entire universes could exist. Imagine our universe as a single slice of bread in an endless loaf, with other branes hovering nearby in higher dimensional space. And sometimes these branes collide. When they do, the energy released could be catastrophic enough to ignite a brand new Big Bang, birthing a fresh universe with its own laws. This isn't science fiction, it's the brane collision scenario, a dramatic twist on cosmic origins. Some physicists even speculate that our own universe's birth might have been triggered by such a collision, a violent, higher dimensional crash that set everything into motion. But the wildest implication, if the string theory landscape is real, then there could be countless other universes out there, some where gravity is stronger, others where atoms never form, and perhaps a few where life blossoms in ways we can't fathom. It's a humbling thought. The rules we consider fundamental might just be local bylaws in a sprawling multiverse. And while we've yet to find concrete evidence for these ideas, they push us to ask bigger questions. What if the universe isn't fine-tuned for life, but life is just lucky to exist in a corner of reality where the numbers lined up? The string theory landscape doesn't just redefine beginnings, it redefines possibility itself. Hold onto your seats because quantum mechanics is about to flip everything you thought you knew about nothingness on its head. What if the universe didn't need a grand explosion or a cosmic collision to get started? What if it just popped into existence all on its own? That's the radical idea behind the quantum fluctuation origin theory, where the rules of the subatomic world rewrite the story of creation itself. At the heart of this idea is a mind-bending truth. Empty space isn't really empty. Even in a perfect vacuum, particles flicker in and out of existence like cosmic fireflies, borrowed from the universe's energy budget for fleeting moments before vanishing again. These quantum fluctuations are tiny, but they hint at something extraordinary, that nothing might be unstable, bubbling with potential energy just waiting to erupt. Physicist Lawrence Krauss took this idea and ran with it in his provocative book, A Universe from Nothing. He argues that the universe could have emerged from a quantum fluctuation on a colossal scale, a random hiccup in the fabric of reality that unleashed enough energy to ignite the Big Bang. Think of it like a cosmic lottery. Against all odds, the universe hit the jackpot, pulling itself out of the quantum void. Krauss even suggests that the total energy of the universe might add up to zero when you account for gravity's negative pull balancing out matter's positive energy. In other words, everything we see, galaxies, stars, even our own bodies, could be the universe's way of balancing its books, a grand cosmic free lunch. But how does this actually work? Enter vacuum energy, the secret source of quantum creation. Even in the absence of matter, space seethes with latent energy, a restless sea of potential thanks to the uncertainty principle. Occasionally, this energy spikes, birthing particles, or, in the case of the early universe, an entire cosmos. Some theories go further, suggesting that our universe might be just one bubble in a frothing multiverse, where countless other universes are constantly blinking into existence, each with its own unique physics. It's a dizzying thought. The greatest show in existence might have started with a quantum whimper, not a bang. And if that's true, then nothingness isn't the end of the story, it's the beginning. What if everything you see around you, the stars, the planets, even your own hands, is nothing more than an incredibly convincing illusion? That's the spine-tingling premise of the holographic principle, a theory so radical it redefines reality itself. Picture this: our three-dimensional universe, with all its depth and complexity, might actually be a hologram, a breathtakingly detailed projection from a two-dimensional surface at the edge of space. It sounds like something ripped from a sci-fi novel, but this idea comes straight from the cutting edge of theoretical physics, championed by minds like Leonard Susskind. The seeds of this theory were planted in the study of black holes, those cosmic enigmas where gravity is so strong not even light can escape. When matter falls into a black hole, it vanishes from our universe, but here's the paradox: according to quantum mechanics, information can never be destroyed. So where does it go? Susskind and others proposed a revolutionary answer. The information isn't lost inside the black hole, but encoded on its event horizon, the point of no return. Think of it like a celestial hard drive, where every bit of data about what fell in is stamped onto the surface in vanishingly tiny pixels. This revelation led to an even wilder thought. If a black hole's interior can be described entirely by information on its boundary, could the same be true for the entire universe? That's the essence of the holographic principle. Just as a credit card's hologram projects a 3D image from a 2D surface, our universe might be a cosmic projection from a flat, distant boundary we can't see. The math behind this is staggeringly complex, rooted in string theory and a concept known as the ad-s/CFT correspondence, which suggests that a higher dimensional space can be perfectly mirrored by a lower dimensional one. To put it in everyday terms, imagine watching a movie on a flat screen. Even though the image appears to have depth, every detail is encoded in the pixels of the screen itself. Our reality could work the same way, with the 3D world we experience being nothing more than a shadow cast by processes happening on a 2D plane. But if this is true, where is this boundary? Some theories place it at the edge of the observable universe, far beyond where light has had time to reach us. Others suggest it's hidden in dimensions we can't perceive. And while we don't yet have direct proof, there are tantalizing hints. Simulations of quantum systems have shown that lower dimensional models can accurately describe higher dimensional behaviors, like a cosmic cheat code that simplifies the universe's most baffling puzzles. The implications are staggering. If the holographic principle holds, it means everything you've ever known, the warmth of sunlight, the taste of food, the vastness of a galaxy, is just an incredibly intricate illusion painted onto the fabric of reality. It's a humbling thought. We might not live in the universe's real version, but in a projection so flawless, we'll never know the difference. And that raises one final, haunting question. If our universe is a hologram, what's casting it? What if the Big Bang wasn't a solitary event, but the aftershock of something far more colossal, a cosmic fender bender between entire universes? That's the jaw-dropping premise of the ekpyrotic universe theory, where our reality isn't born from a singularity, but from the violent collision of two higher dimensional membranes, or branes, drifting through an unseen void. Picture this: our entire universe is like a sheet of paper floating in a vast, dark ocean, and another parallel brane, another sheet, slams into it with unimaginable force. The energy of that crash doesn't just create ripples, it ignites the fiery expansion we call the Big Bang, seeding matter, energy, and the very fabric of spacetime itself. This idea isn't just speculative poetry, it's grounded in string theory's most audacious predictions. Physicists Paul Steinhardt and Neil Turok, the architects of this model, proposed that these branes aren't static. They're dynamic, oscillating entities drawn together and pulled apart by forces we can't yet detect. Each collision between them resets the cosmic clock, birthing a new universe in a cycle that could have repeated endlessly. Unlike inflation, which stretches the universe smooth, the ekpyrotic scenario suggests that the uniformity of our cosmos comes from these branes being nearly identical before impact, like two panes of glass pressed together so evenly they leave no gaps. But here's where it gets even stranger. The ekpyrotic universe might solve one of the Big Bang's biggest puzzles. Why didn't the universe tear itself apart with gravitational chaos? Inflation answers this with rapid expansion, but the brane collision offers a different fix. The energy of the crash would have been focused along a single dimension, the direction of the collision, leaving the others smooth and stable, like shaking a rug without disturbing the floor beneath it. This could explain why our universe appears so finely tuned without the gravitational waves or defects other theories predict. Yet the most tantalizing part: if the ekpyrotic model is right, another collision could happen again. Some versions of the theory suggest these brane crashes aren't one-off events, but part of an eternal rhythm, with universes endlessly reborn in cosmic symphonies of destruction and creation. It's a humbling thought. The universe we call home might just be the latest episode in a multiverse-spanning saga, where every ending is a prelude to another spectacular beginning. Of course, not all physicists are convinced. Critics point out that we've yet to detect direct evidence of these higher dimensional branes or the gravitational echoes such a collision would leave behind. But whether or not the ekpyrotic universe holds up, it challenges us to think bigger, to imagine origins not as a single spark, but as a cosmic dance of dimensions we're only beginning to glimpse. And if Steinhardt and Turok are right, the next chapter of our universe's story might already be written, waiting on the other side of an invisible divide. Roger Penrose's conformal cyclic cosmology doesn't just imagine a universe reborn, it rewrites the rules of death and resurrection on a cosmic scale. Picture this: trillions of years from now, when the last black holes have evaporated and the universe is nothing but a sea of lifeless radiation, something extraordinary happens. The vast, cold emptiness reaches a state so uniform, so stretched thin, that it becomes mathematically identical to the hot, dense singularity of a new Big Bang. Time itself loses meaning as the universe forgets its own scale, looping back to begin again in an endless cycle of cosmic reincarnation. This isn't science fiction, it's a daring mathematical twist where the far future becomes the distant past through a process called conformal rescaling. The key to this eerie symmetry lies in black holes, or rather, what they leave behind. According to Stephen Hawking's groundbreaking work, black holes aren't eternal. They slowly leak energy, radiating themselves away over incomprehensible timescales until they vanish in a final puff of particles. Penrose takes this idea and flips it into something revolutionary. Those last bursts of Hawking radiation might carry imprints of the previous universe, seared into the fabric of space-time like cosmic graffiti. When the next cycle begins, these imprints could reappear as faint, circular patterns in the cosmic microwave background, ghostly echoes of ancient black holes from a reality long gone. That's exactly what Penrose claims to have found. Along with colleagues, he's pointed to unusual, ring-shaped features in the CMB, dubbing them Hawking points in honor of his late friend. These anomalies, he argues, are too precise to be random noise. They're the thermal fingerprints of supermassive black holes from a predecessor universe, their final screams stretched across the sky by the birth of our own cosmos. It's a poetic idea. The very objects that once devoured light might have become the midwives of a new beginning. Not everyone's convinced, of course. Critics argue these patterns could just be statistical flukes, cosmic static masquerading as something profound. The Planck satellite, which mapped the CMB in unprecedented detail, found no conclusive evidence for Penrose's rings. And some physicists question whether conformal rescaling, the mathematical sleight of hand that makes the cycle possible, even works in the messy, particle-filled reality we inhabit. But Penrose's model thrives on these challenges, daring us to imagine a universe where endings are illusions and every collapse plants the seed for a new explosion of existence. What's truly staggering is the timescale. Each eon, as Penrose calls these cosmic cycles, could last a googol years or more, numbers so vast they dwarf the current age of our universe. And yet, through the lens of conformal cyclic cosmology, those eons are just heartbeats in an infinite rhythm. It's a vision that renders beginnings and endings meaningless, replacing them with something far more profound. A universe that never truly dies, but simply sheds its skin over and over again, wearing its past like a whisper in the static of the sky. Whether the Hawking points are real or not, this theory forces us to confront a humbling truth. We might not just be living in one universe, but standing on the shoulders of giants we'll never see. What if the universe didn't start with a bang at all, but with a bounce? Loop quantum gravity dares to rewrite the cosmic origin story by suggesting spacetime itself is woven from tiny, indivisible threads, so finely stitched that not even the crushing density of a singularity can tear them apart. Unlike string theory, which dreams of hidden dimensions and vibrating strings, this framework keeps its feet firmly in the observable universe, proposing that space and time aren't smooth and continuous but pixelated, a cosmic fabric woven from discrete, quantum-sized loops. These loops are so unimaginably small, they defy measurement, but their existence could solve one of cosmology's biggest headaches: the Big Bang singularity, that infinitely dense, infinitely hot point where all known physics breaks down. Here's the game changer. In loop quantum gravity, there's no such thing as true infinity. When you rewind the universe back to its earliest moments, gravity doesn't spiral out of control, it hits a limit. Picture squeezing a spring. The harder you press, the more it resists until it finally pushes back. Similarly, as matter and energy collapse toward the singularity, quantum effects kick in like a cosmic safety net, preventing total collapse. Instead of a violent beginning, the universe might have rebounded from a previous contraction, a big bounce, that transformed a dying cosmos into the one we see today. It's a radical reimagining of cosmic history, where time doesn't begin, it just cycles, like a celestial pendulum swinging between expansion and contraction. This bounce isn't just poetic symmetry, it's backed by math. Equations in loop quantum gravity suggest that as the universe approaches its maximum density, quantum corrections flip gravity from an attractive force to a repulsive one, triggering an explosive rebound. No unknowable singularity, no boundaries of time, just a seamless transition from one era to the next. And if this model holds, it could leave fingerprints in the cosmic microwave background. Faint ripples from the pre-bounce universe, echoes of a cosmos that came before ours. Some researchers even speculate these patterns might already be hiding in data we've collected, waiting to be decoded. But loop quantum gravity isn't without its rivals. String theory's extra dimensions and holographic universes grab headlines, while this approach stays grounded in 4 dimensions, focusing on what we can observe. Yet that simplicity might be its strength. By quantizing spacetime itself, it offers a way to marry Einstein's relativity with quantum mechanics without invoking unseen dimensions or untestable branes. It's a reminder that sometimes the most revolutionary ideas aren't the flashiest, they're the ones that force us to rethink the very fabric of reality, one tiny loop at a time. Whether the big bounce is real or not, this theory challenges us to imagine a universe where endings are just new beginnings in disguise. Forget everything you've been told about gravity reigning supreme in the early universe, because Hans Alfvén's plasma universe theory flips the script entirely. This Nobel Prize-winning physicist dared to suggest that electromagnetism, not gravity, was the dominant force shaping the cosmos in its infancy. Picture a universe not of serene cosmic expansion, but of crackling electric currents and swirling plasma filaments, a vast electrified tapestry where magnetic fields sculpted galaxies long before gravity took center stage. At the heart of this idea is plasma itself, the 4th state of matter, an electrified soup of ions and free electrons that makes up over 99% of the visible universe. Alfvén argued that in the early cosmos, before stars and galaxies formed, this plasma wasn't just passive background noise. It was alive with currents twisting into colossal structures called Birkeland currents, named after his colleague Christian Birkeland. These aren't just theoretical quirks. We see them today in the auroras dancing at Earth's poles, where charged particles spiral along magnetic field lines. Now, imagine that same process scaled up to cosmic proportions, with filaments of plasma stretching across light years. Their electromagnetic forces organizing matter into the seeds of future galaxies. The implications are staggering. Mainstream cosmology credits gravity with pulling gas clouds into galaxies, but plasma cosmology suggests those clouds were already pre-shaped by electromagnetic forces. Picture a river carving a canyon. Gravity might have deepened the valley, but the plasma's currents laid down the original channels. This isn't just a minor tweak to the Big Bang model. It's a full-blown alternative, one where galaxy clusters align along invisible power lines of cosmic electricity, and where the universe's large-scale structure reflects an electromagnetic fingerprint rather than a gravitational one. Critics, of course, have pushed back. The plasma universe theory struggles to explain the cosmic microwave background's near-perfect uniformity, a cornerstone of Big Bang cosmology. And while lab experiments confirm plasma's behavior at small scales, extrapolating those rules to the entire universe remains controversial. But Alfvén's work has left an indelible mark. Modern astrophysicists now recognize the role of plasma in shaping nebulae, powering solar flares, and even influencing galaxy formation, a quiet vindication of his once heretical views. What's most tantalizing is how this theory reframes our place in the cosmos. If Alfvén was right, the universe isn't just a cold, dark expanse punctuated by islands of matter. It's a dynamic electrical network humming with energy and structure at every scale. It's a reminder that sometimes the most powerful forces aren't the ones we can see, but the invisible currents stitching reality together. And that raises a provocative question. Could electromagnetism still be quietly shaping the universe today, hiding in plain sight between the stars? What if every black hole isn't just a cosmic dead end, but a secret doorway to a brand new universe? Lee Smolens's explosive idea, dubbed cosmic natural selection, turns black holes from celestial graveyards into cosmic maternity wards, where the collapse of one universe births another. Picture this: when a star collapses into a black hole, the unfathomable crush of gravity at its core doesn't stop at a singularity. Instead, it triggers a quantum rebound, a moment of such extreme physics that spacetime itself flips inside out, exploding outward in a new Big Bang. Our universe, then, could be the offspring of a black hole in some higher dimensional parent cosmos, and every black hole in our own reality might be incubating countless others. It's a dizzying chain of celestial lineage where universes evolve not through random chance but through a form of cosmic Darwinism. Smolens's theory doesn't stop there. He proposes that this process isn't just creative, it's competitive. Universes that produce more black holes have more children, passing on their physical laws like genetic traits. Over eons, this could favor universes with constants fine-tuned for black hole production, explaining why our own cosmos seems oddly optimized for their creation. Think of it like a cosmic game of survival of the fittest, where the rules of physics aren't arbitrary, but honed by countless generations of trial and error. The speed of light, the strength of gravity, these might not be accidents, but the result of a brutal, universe-spanning selection pressure. But how could we ever test such a wild idea? One clue might lie in the very fabric of reality. If black holes truly birth universes, the conditions inside them could leave subtle imprints on the laws of their offspring. Some physicists speculate that these inherited traits might manifest as tiny deviations in fundamental constants, or patterns in the cosmic microwave background, cosmic ancestry written in the sky. Others argue that if Smolens's right, our universe should be maximally efficient at producing black holes, a prediction that could be checked against observations of star formation and galaxy collisions. Of course, not everyone's convinced. Critics point out that without direct evidence of these daughter universes, the theory remains speculative, a beautiful idea still waiting for its smoking gun. And then there's the philosophical kicker. If every black hole spawns a new cosmos, what does that say about our own universe's origins? Are we the product of some long-forgotten cosmic ancestor's gravitational collapse? Smolens's vision blurs the line between physics and mythology, offering a story where destruction and creation are two sides of the same coin, and where the darkest objects in the cosmos might just be the brightest beacons of new beginnings. What if the universe isn't a cosmic accident or a grand cycle of rebirth, but something far stranger, a simulation meticulously coded by an advanced civilization? This isn't just the plot of a sci-fi movie, it's a legitimate hypothesis debated by philosophers and physicists alike. At its core, simulation theory suggests that everything we experience, the stars, the laws of physics, even our own consciousness, might be nothing more than lines of code in an unfathomably complex digital construct. Think of it like the most immersive video game ever conceived, where we're not players but characters programmed to believe we're real. Philosopher Nick Bostrom gave this idea a razor-sharp framework with his now famous trilemma. He argues that at least one of these statements must be true. 1. Almost all civilizations at our level of technological development go extinct before they can create simulations. 2. If any civilization reaches the capability to simulate universes, they choose not to. Or 3. We're almost certainly living in a simulation. The logic is chillingly simple. If even one advanced civilization avoids extinction and decides to run ancestor simulations, digital recreations of their past, the number of simulated minds would vastly outnumber the biological ones. Statistically, the odds tilt heavily toward us being among the simulated. This isn't just philosophical sleight of hand. The Fermi paradox, the eerie silence of the cosmos despite its apparent readiness for life, finds an unsettling answer in simulation theory. Where are all the aliens? Maybe they're absent because the simulators deliberately coded them out, trimming unnecessary complexity to conserve computational resources. After all, rendering an empty universe is far more efficient than one teeming with interstellar civilizations. Or perhaps we're in some kind of cosmic zoo, a controlled experiment where the parameters are tweaked to study our behavior. But could we ever prove we're in a simulation? Some physicists suggest looking for glitches, tiny imperfections in reality that might betray its digital nature. Like a video game with pixelation at the edges, the universe might have resolution limits, detectable in high-energy particle collisions or anomalies in quantum mechanics. Others propose that if the simulation runs on a finite system, the speed of light might actually be a processing speed limit, and Planck length, the smallest possible unit of space, could be the pixel size of reality itself. Of course, not everyone's convinced. Critics argue that simulating every particle in the universe would require energy and computational power beyond any conceivable technology, even for an ultra-advanced civilization. But what if the simulators cheat? Just as video games render only what the player sees, our universe might be a just-in-time illusion, with details filled in only when observed, a cosmic-level version of the quantum observer effect. Simulation theory forces us to confront existential questions we can't unask. If we're in a simulation, do our choices matter? Are the simulators gods, scientists, or something beyond our comprehension? And if we one day create our own simulations, does that make us both the simulated and the simulators, a matryoshka doll of realities nested inside realities? Whether it's true or not, this idea shatters our assumptions about existence, leaving us to wonder, if the universe is a program, who or what wrote the code? At the dawn of the universe, before stars ignited and galaxies took shape, an invisible symphony of particles may have played the most pivotal role in existence, particles we've yet to discover. Supersymmetry, or SUSY, isn't just another elegant theory. It's a potential master key to the cosmos, suggesting every known particle has a hidden, heavier twin we've never seen. These shadowy partners, photons, quarks, selectrons, could have been the universe's first architects, shaping the delicate balance between matter and antimatter that made our reality possible. Picture the early cosmos as a seething, chaotic storm of energy, where particles and antiparticles annihilated each other in flashes of radiation. For every quark born, there should have been an antiquark, a perfect symmetry that would have left the universe empty, devoid of matter. But here we are, in a world built from stars, planets, and life itself. How did matter win? Sussy offers a tantalizing answer. Those yet undetected superpartners might have tipped the scales. In those first moments, as supersymmetric particles decayed, they could have done so with a slight preference for matter over antimatter, leaving behind just enough protons and electrons to build everything we see. It's like rolling a loaded die. One side comes up just a fraction more often, and over billions of interactions, that tiny bias changes everything. The math behind this is staggeringly beautiful. Sussy doesn't just patch up the matter-antimatter problem. It weaves gravity into the quantum realm, bridging two theories that have stubbornly resisted unification. Those heavy superpartners could explain dark matter. Two neutralinos, a hypothetical Sussy particle, might be the invisible glue holding galaxies together right now. Imagine the same particles that saved the universe from self-destruction could still be out there, silently shaping its structure. Yet for all its promise, Sussy remains a ghost. Despite decades of searching, the Large Hadron Collider hasn't found conclusive evidence of these superpartners at the energies we've probed. Some theorists wonder if Sussy particles are simply too heavy for our current machines, lurking just beyond reach. Others suggest Sussy might manifest in ways we haven't anticipated, or that nature chose a different path entirely. But even without direct proof, the theory's elegance keeps it alive. It solves too many puzzles at once to dismiss, a cosmic multitool that could explain everything from the Higgs boson's mass to the universe's very existence. The suspense is part of the thrill. If Sussy is real, it means the universe operates on a mirror principle we've barely glimpsed, with entire layers of reality waiting to be uncovered. And if not, well, the hunt for answers will lead us somewhere even stranger. After all, the greatest mysteries are the ones that refuse to give up their secrets easily. What if time as we know it, that steady, one-way march from past to future, is nothing more than an illusion? Julian Barber's radical vision of timeless physics suggests just that, proposing a universe where clocks are mere human inventions and before and after are relics of our limited perception. Imagine reality not as a movie playing frame by frame, but as a vast, frozen sculpture where every possible configuration of the cosmos exists simultaneously, from the Big Bang to the heat death of everything. In Barber's framework, what we call the flow of time is just our brains stitching together static snapshots, like flipping through a cosmic flipbook. It's a dizzying thought. The universe might not happen, it simply is, with all moments equally real and eternally present. But how does this explain the undeniable feeling of time passing? Barber points to the peculiar structure of the universe itself. Think of a mountain range where each peak represents a moment of high complexity, like a living, conscious observer, and the valleys between them are simpler, less ordered states. Our perception of time emerges as we hop from one peak to another, mistaking this journey for a continuous flow. It's not that time moves, it's that we're navigating a landscape of frozen instants, convinced we're watching a story unfold when we're really just wandering through an infinite gallery of nows. Sean Carroll takes a different but equally mind-bending approach. His two-directional time model dares to ask, why does time only flow forward? At the quantum level, the laws of physics work just as well backward as forward, yet we never see shattered cups reassemble or smoke retreating into cigarettes. Carroll argues that the Big Bang wasn't time's starting gun, it was a mirror reflecting another universe where time runs in reverse. Picture two cosmic bubbles expanding outward from a central point, one moving forward in time, the other backward. From our perspective, entropy always increases, creating the arrow of time we experience, but from the other universe's viewpoint, we're the ones moving backward. The implications of these theories are staggering. If Barber is right, the question, what happened before the Big Bang, becomes meaningless. There was no before, only a timeless tapestry where the Big Bang is one thread among infinite others. Carroll's model, meanwhile, suggests the Big Bang was less a beginning and more a turning point, a cosmic pivot where time split into two symmetrical branches. Both ideas challenge our deepest assumptions about reality. Could it be that time, like gravity or light, is just another force we've misunderstood, or that our stubborn belief in its linearity blinds us to a universe far stranger than we've dared to imagine? The search for answers isn't just philosophical, it's etched into the fabric of the cosmos. Some physicists look for clues in quantum entanglement, where particles seem to communicate instantaneously across space, as if time doesn't apply. Others study black holes, where time itself slows to a crawl at the event horizon, hinting at its malleability. And if these theories hold, they could rewrite not just cosmology, but our understanding of consciousness, free will, and even the nature of existence. After all, if time is an illusion, what does that make us? The fleeting patterns convinced we're moving through it. The universe, it seems, still has a few timeless secrets left to share. Dark matter doesn't just lurk unseen in the cosmos. It might have been the invisible hand that sculpted the universe's first moments. While we still don't know what dark matter is, we know its gravitational pull shapes galaxies and bends light. But what if its influence runs even deeper, reaching back to the universe's explosive infancy? Some theorists propose that dark matter didn't just respond to cosmic evolution. It may have driven it, acting as a hidden catalyst for inflation or the birth of cosmic structures. Imagine a cosmic domino effect. As dark matter particles clumped together in the early universe, their gravity could have created the tiny density fluctuations that inflation later magnified into galaxies. Without those initial seeds, the universe might have remained smooth and featureless, a cosmic blank canvas with no stars, no planets, no us. Here's where it gets even stranger. Dark matter's ghostly nature means it doesn't interact with light or ordinary matter the way atoms do. This could have given it a head start in the cosmic structure race. While normal matter was too busy bouncing off radiation in the hot, dense early universe, dark matter could have been quietly coalescing into vast, invisible scaffolds. These dark matter wells would then act like gravitational traps, pulling ordinary matter into them once it finally broke free from radiation's grip. Think of it like a cosmic construction crew laying the foundation in the dark, with visible matter just showing up later to fill in the walls. But could dark matter have also kick-started inflation itself? One provocative idea suggests that a unique type of dark matter particle, one that decays or interacts in just the right way, could have released the burst of energy needed to trigger the universe's hyper-expansion. Picture a pressure cooker with a hidden release valve. As these particles broke down, they might have unleashed a surge of repulsive gravity, sending space-time into overdrive. It's a tantalizing thought that the very substance we're still struggling to detect could hold the key to the universe's most dramatic growth spurt. Of course, not all models agree. Some argue that dark matter's role came later, after inflation had already done its job. Others propose that dark matter and inflation are entirely separate cosmic players, their stories intersecting only by chance. But the possibility remains, dark matter might not just be a passive bystander in cosmic history, but the hidden architect of everything we see. And if that's true, then every galaxy, every star, even our own existence, could owe itself to the gravitational whispers of something we've never even seen. What's most thrilling is that we might be on the verge of answers. Next-generation telescopes and particle detectors are hunting for dark matter's fingerprints, from subtle warps in spacetime to rare particle collisions deep underground. If we can finally unmask this cosmic ghost, we won't just be solving a modern mystery, we might be rewriting the universe's origin story itself. Because sometimes the most powerful forces aren't the ones we can see, but the ones that work in the shadows, pulling the strings of reality from the very beginning. Phantom energy isn't just pushing the universe apart, it's threatening to shred the very fabric of reality itself. Picture this: dark energy, the mysterious force accelerating cosmic expansion, isn't constant. Some theories suggest it could grow stronger over time, becoming something far more sinister. Phantom energy. Unlike ordinary dark energy, which gently stretches space-time, phantom energy would escalate uncontrollably, its repulsive force amplifying until galaxies, stars, even atoms are torn asunder in a cataclysmic finale called the Big Rip. Here's how it would unfold. Right now, the universe's expansion is already pulling galaxies away from each other, but gravity keeps local structures like our Milky Way intact. Phantom energy changes the game. As it intensifies, its pressure wouldn't just overcome gravity, it would overpower every fundamental force, from electromagnetism to the nuclear bonds holding matter together. First, galaxy clusters would be ripped apart, then individual galaxies. Stars would be plucked from their orbits, planets wrenched away from their suns. In the final moments, atoms themselves would disintegrate, their nuclei torn apart by the exponential stretching of space. It's not just an end, it's an unmaking, a universe unraveling at the seams. The timeline is as terrifying as the scenario. If phantom energy exists, some models suggest the Big Rip could happen in as little as 20 billion years, a cosmic blink compared to the universe's current age. For context, Earth will likely be swallowed by the Sun's expansion long before then, but the idea that spacetime itself has an expiration date is chilling. And yet, there's a bizarre twist. Some theorists propose that the Big Rip might not be the end, but a reset. If spacetime is torn apart with enough violence, the energy released could trigger a new Big Bang, birthing another universe from the ashes of the old one. The evidence for phantom energy is speculative but haunting. Observations of distant supernova and the cosmic microwave background hint that dark energy's strength might not be perfectly constant. If those fluctuations trend upward, phantom energy becomes a real possibility. It's as if we're driving a car with an accelerator stuck to the floor, except the car is the universe and the brakes don't exist. What's perhaps most unsettling is the randomness of it all. If phantom energy is real, its emergence wasn't planned or inevitable, just a roll of the cosmic dice. One day, without warning or malice, the universe might decide to erase itself in the most violent way possible. But in that destruction lies a strange hope. From the wreckage of one cosmos, another could rise, carrying forward the eternal cycle of creation and destruction. Whether that's solace or just another cosmic irony depends on how you look at it, assuming there's anyone left to look at all. Imagine a universe that lasts forever, not just billions or trillions of years, but an eternity stretching endlessly in all directions. Now consider this unsettling possibility. In that infinite canvas of time and space, randomness could conjure up something even stranger than galaxies or black holes, a fully formed, self-aware consciousness emerging spontaneously from the chaos. No birth, no evolution, just a flicker of awareness popping into existence like a cosmic glitch. This isn't science fiction, it's the bizarre thought experiment known as the Boltzmann brane, and it might be one of the most unsettling ideas in all of physics. The concept traces back to Ludwig Boltzmann, the 19th century physicist who revolutionized our understanding of entropy. He realized that in an infinite universe, even the most improbable events become inevitable given enough time. Flip a coin enough times and eventually you'll get a million heads in a row. Extend that logic to reality itself and suddenly, the spontaneous assembly of atoms into a thinking, observing mind complete with false memories of a past that never happened doesn't seem so far-fetched. In fact, statistically, these disembodied observers should outnumber ordinary, biologically evolved minds like ours by an unimaginable margin. Here's the existential kicker. If Boltzmann brains are possible, how do we know we're not one of them? Right now, you might feel certain of your own history, the childhood memories, the relationships, the passage of time. But in a universe where randomness can craft entire identities from nothing, that certainty crumbles. Your sense of self could be an illusion, a fleeting arrangement of particles that just thinks it has a lifetime of experiences. It's a cosmic version of the brain in a vat scenario, except the vat is the universe itself, and the brain might blink out of existence as suddenly as it appeared. This paradox isn't just philosophical, it's a direct challenge to our theories of cosmology. If the universe truly tends toward disorder, why do we see so much structure? Why aren't Boltzmann brains the dominant observers, drowning out real minds like ours? Some physicists argue this very problem undermines certain models of eternal inflation or cyclical universes, forcing us to rethink whether infinity is even compatible with what we observe. After all, if the math predicts a universe teeming with disembodied minds over fleshy, evolved ones, yet we're clearly here, something might be fundamentally wrong with the math. But there's a twist. The Boltzmann brain dilemma might actually be evidence against an eternal universe. If eternal inflation or steady-state models inevitably lead to these phantom observers, yet we don't see them, perhaps the universe isn't infinite after all. Maybe it has a finite lifespan, cutting off the time needed for such absurdly improbable events to occur. Or perhaps consciousness can't arise from pure randomness. It might require the precise, iterative scaffolding of evolution, making Boltzmann brains impossible no matter how much time passes. This idea forces us to confront the fragility of our assumptions. We take for granted that our perceptions are real, that the past happened, that we're more than cosmic coincidences. But the Boltzmann brain reminds us that reality might be far stranger, far more precarious than we ever imagined. And while we'll likely never meet one of these hypothetical minds, their shadow lingers over every question about the universe's beginning, its end, and what it truly means to exist in between. Black holes devour everything in their path, but what if their opposites, white holes, could be the cosmic firestarters that birthed our universe? Imagine a black hole in reverse. Instead of sucking matter in, a white hole violently expels it, spewing out energy and space like an unstoppable cosmic geyser. Now take that idea and stretch it to the ultimate extreme. What if the Big Bang wasn't an explosion from nothing, but the spectacular eruption of a white hole in another universe? This isn't just wild speculation, it's a serious hypothesis explored by physicists like Carlo Rovelli, who see these mysterious objects as potential keys to unlocking the universe's origins. Rovelli's work in loop quantum gravity suggests something astonishing. When black holes reach the end of their lives, they might not vanish completely. Instead, they could undergo a quantum transformation, rebounding as a white hole in a burst of new spacetime. Picture a dying star collapsing into a black hole, compressing to unimaginable densities. But instead of forming a singularity, quantum effects kick in like a cosmic trampoline, bouncing the collapsing matter back outward as a white hole. The energy of that rebound could be cataclysmic enough to ignite an entirely new universe, birthing a fresh cosmos from the corpse of an old one. The implications are staggering. If this is true, our universe might not be the first, it could be the offspring of a black hole in some parent reality, with every black hole in our own cosmos potentially incubating another. It's a cosmic matryoshka doll of universes, each nested inside the other. And here's the twist, this idea could solve one of the biggest puzzles in physics, the black hole information paradox. If black holes don't destroy information but instead encode it in the white hole's explosion, then the universe might preserve its history in ways we're only beginning to grasp. But how would we ever test something like this? Some theorists look for clues in the cosmic microwave background, searching for imprints of a pre-Big Bang universe. Others suggest that if our cosmos was born from a white hole, its initial conditions might carry faint echoes of its parent's physics, like a cosmic fingerprint hidden in the distribution of galaxies. There's even speculation that tiny, short-lived white holes might still pop into existence today, flaring briefly like cosmic firecrackers before vanishing again. Of course, not all scientists are convinced. White holes remain purely theoretical, and the math governing their behavior is notoriously slippery. Some argue that if they existed, we'd have seen evidence by now, unless, of course, they're hiding in plain sight as the Big Bang itself. Whether Ravelli's vision holds up or not, it forces us to rethink the boundaries of reality. The universe might not have started with a bang, but with a bounce, an explosive second act to a black hole's tragic finale. And if that's true, then the darkest objects in the cosmos might just be the brightest beacons of creation. Gravity has always been the universe's great architect, sculpting galaxies and bending light with its invisible hand. But what if we've been thinking about it all wrong? Eric Verland's entropic gravity theory flips the script entirely, suggesting gravity isn't a fundamental force at all. It's an illusion, a side effect of something far more primal: entropy, the universe's relentless slide into disorder. Picture this: the fabric of spacetime isn't governed by Newton's equations or Einstein's curvature, but by the statistical tendency of microscopic building blocks to arrange themselves in the most probable configurations. Gravity, in this view, becomes a kind of cosmic friction, emerging from the way information reshuffles itself at the quantum level. Verland's idea builds on a radical insight. When particles move, they don't just traverse space, they nudge the universe's hidden information structure, creating what we perceive as gravitational attraction. Think of it like a crowd at a concert. If one person shifts position, others instinctively adjust to maintain balance. In the same way, mass might not create gravity directly. Instead, it disrupts the entropy of underlying quantum bits, and gravity emerges as the system rebalances. This isn't just poetic metaphor. The math suggests this approach could explain the motions of galaxies without invoking dark matter, rewriting one of cosmology's biggest mysteries. Now, rewind to the universe's first moments. If gravity is entropic, those initial instants weren't dominated by a battle between forces, but by a chaotic dance of information scrambling to maximize entropy. The Big Bang's explosive expansion might not have been driven by repulsive gravity or inflation, but by the universe's quantum bits seeking equilibrium, like a deck of cards shuffling itself at blinding speed. Even the fabric of spacetime itself could be a holographic projection of this deeper information layer, a cosmic spreadsheet updating itself trillions of times per second. Critics argue that entropic gravity remains untested, lacking the precise predictions that made relativity and quantum mechanics so revolutionary. But Verland's framework offers something tantalizing: a bridge between gravity and quantum mechanics, two pillars of physics that have stubbornly resisted unification. If he's right, the universe's first moments weren't governed by forces, but by statistics, a game of probability played on the grandest scale imaginable. And that changes everything. Suddenly, the cosmos isn't a machine governed by immutable laws, but a vast, evolving computation, where even gravity is just a shadow of something far more profound. The implications ripple outward. If gravity emerges from entropy, then black holes, those cosmic entropy factories, might hold the key to understanding its true nature. Dark energy could be the universe's way of balancing its informational ledger, and the arrow of time, perhaps it's not just a thermodynamic quirk, but the very engine behind spacetime's structure. Verland's theory is still young, but it dares us to rethink reality's deepest foundations. After all, if gravity is just a side effect, what other fundamental forces might be illusions waiting to be unraveled? The universe should have annihilated itself at birth. That's the chilling conclusion when you realize matter and antimatter were created in nearly equal amounts during the Big Bang. Every particle of matter had its antimatter twin, ready to collide and vanish in a burst of pure energy. Yet here we are in a cosmos made almost entirely of matter, with antimatter vanishingly rare. How did this cosmic imbalance happen? The answer lies in baryogenesis, one of physics' most tantalizing puzzles, where the tiniest asymmetry in nature's laws tipped the scales toward our existence. At the heart of this mystery are the three Sakharov conditions, named after Soviet physicist Andrei Sakharov, who laid out the blueprint for how matter could dominate. First, the universe needed a process that treated matter and antimatter differently, something called CP violation. Normally, the laws of physics are symmetric. Swapping particles for antiparticles and mirroring their motions should leave interactions unchanged. But in rare cases, like certain decays of kaon and B meson particles, this symmetry breaks. The universe, it seems, has a subtle preference for matter, a bias so small it's like flipping a coin that lands heads up 50,00001% of the time. Over billions of particle interactions, that microscopic imbalance snowballed into the matter-dominated cosmos we see today. The second condition demands the universe was once hot and dense enough for these asymmetrical processes to occur. In the seething chaos just after the Big Bang, particle collisions happened at energies so high they're impossible to recreate even in our most powerful colliders. This was a time when the four fundamental forces might have been unified, and exotic particles now long vanished could have interacted in ways that favored matter. As the cosmos cooled, those fleeting opportunities slammed shut, locking in the matter surplus we now inherit. Finally, Sakharov realized the universe couldn't be in equilibrium. It had to be out of balance, like a snow globe still swirling after being shaken. If matter and antimatter had reached thermal equilibrium, they would have annihilated completely, leaving nothing but radiation. Instead, the universe's rapid expansion froze in the asymmetry before it could be erased, like a snapshot of a coin mid-toss, forever capturing the moment it leaned toward matter. But how exactly did CP violation tip the scales? Enter leptogenesis, a twist where neutrinos, those ghostly particles that barely interact with matter, could be the unsung heroes. According to this theory, ultra-heavy neutrinos in the early universe decayed unevenly, producing slightly more matter than antimatter. These decays would have also emitted the lightweight neutrinos we detect today, weaving a thread connecting the universe's first moments to the particles streaming through your body right now. It's a cosmic sleight of hand. Neutrinos, almost invisible to detectors, might hold the key to why anything exists at all. Yet gaps remain. The observed CP violation in particle physics is thousands of times too weak to explain the universe's matter surplus. This discrepancy hints at undiscovered particles or forces lurking beyond our current models, perhaps accessible only at energies akin to the Big Bang itself. Some theorists turn to supersymmetry, hoping undiscovered partner particles could amplify the asymmetry. Others explore the idea that antimatter domains might hide in distant corners of the cosmos, though searches have turned up empty so far. What's clear is that baryogenesis isn't just a footnote in cosmology, it's the reason we're here. Without that fragile, 1 in a billion imbalance, stars wouldn't shine, planets wouldn't form, and life would never have gotten its chance. The universe's preference for matter might be the ultimate example of winning the cosmic lottery, and the jackpot, everything you've ever known. What if the universe's first moments didn't just birth stars and galaxies, but also countless tiny black holes, so small they could fit in your hand, yet so dense they outweigh mountains? These aren't the monstrous black holes we know today, but primordial black holes, hypothetical relics from the universe's infancy that could solve two of cosmology's biggest puzzles: dark matter and the rapid growth of galaxies. Imagine the early cosmos as a roiling pressure cooker. where fluctuations in density were so extreme that some regions collapsed directly into black holes, no dying stars required. These ancient objects might have formed in the first second after the Big Bang, when the universe was hot enough to squeeze matter into microscopic knots of spacetime. Their size could range from subatomic to asteroid scale, but their impact would be colossal. Unlike their stellar mass cousins, primordial black holes wouldn't evaporate quickly, they'd linger, drifting through the cosmos like invisible ghosts. And here's the kicker: if enough of them exist, they could be the dark matter we've been searching for. Think about it. Dark matter doesn't emit light, barely interacts with normal matter, and clusters around galaxies exactly how you'd expect a swarm of primordial black holes to behave. Some could still be out there today, silently weaving through the Milky Way, their gravity tugging on stars and bending light just like the dark matter we infer but can't see. But the story gets even wilder. These tiny titans might have jump-started the universe's first galaxies. In the early cosmos, gas clouds needed something to act as gravitational seeds, clumping together fast enough to form stars before expansion diluted everything. Ordinary matter alone was too sluggish, but primordial black holes, they'd have been the ultimate cosmic anchors, their intense gravity pulling in surrounding gas like magnets. A single marble-sized black hole could have grown into a quasar's heart, its appetite fueling the birth of a galaxy. It's a cosmic domino effect: first black holes, then stars, then galaxies, all sprouting from seeds sown in the universe's first breath. The hunt for these elusive objects is already underway. Some scientists scour old neutron star data for telltale flashes, signs a primordial black hole might have collided with one, releasing a burst of energy. Others study the subtle flickering of distant stars, watching for moments when a black hole's gravity briefly magnifies their light like a lens. Even gravitational wave detectors might catch the ripples from two primordial black holes spiraling together, a collision echoing from the dawn of time. Yet the theory isn't without its skeptics. If primordial black holes were everywhere, why haven't we seen more direct evidence? Some models suggest they disrupt star clusters or warp cosmic backgrounds in ways we haven't observed. But that hasn't killed the idea, just refined it. Maybe only a fraction of dark matter is primordial black holes, or they exist in mass ranges we haven't probed yet. Whether they're real or not, these cosmic fossils force us to rethink the universe's infancy. If confirmed, they'd be a stunning reminder that the smallest things can have the largest consequences, and that the answers to our biggest mysteries might be hiding in the shadows of the very first moments. Before particles had names, before quarks, electrons, or even photons, there might have been an era where reality belonged to one elusive ruler, the neutrino. These ghostly particles, so insubstantial they pass through entire planets like they're not even there, could have once dominated the cosmos in a primordial sea of unimaginable density. Picture a universe before the Big Bang, not as empty nothingness, but as a churning ocean of neutrinos, their collective mass and interactions setting the stage for everything that followed. In this hypothetical neutrino epoch, temperatures and energies would have been so extreme that particles we consider fundamental today might have been mere fragments of something grander. Neutrinos, which now barely tip the scales, could have been thousands of times heavier in those first moments, their decays shaping the hierarchies of mass and energy we now take for granted. It's like discovering the ruins of an ancient civilization and realizing their decisions still govern our modern world. The tiny, nearly weightless neutrinos we detect today might be the faded remnants of their former glory, like echoes of a forgotten cosmic dynasty. The implications ripple through modern physics. If neutrinos once ruled, their interactions could explain why matter won out over antimatter. Their asymmetrical decays might have sprinkled just enough extra particles into the universe to tip the balance, making stars, planets, and life possible. Even the mysterious dark matter could have ties to this era. some theories suggest sterile neutrinos, a hypothetical heavier cousin of the ones we know, might be hiding in plain sight as the invisible glue holding galaxies together. But how could something so feeble today have ever been so powerful? The key lies in symmetry breaking. As the universe cooled, the forces governing particles split apart like ice crystallizing from water. Neutrinos, once on equal footing with quarks and electrons, might have lost their dominance as this cosmic phase transition locked in the rules we see now. It's as if the universe started with all possible instruments playing at once, then silenced most of them, leaving only the faintest hum of neutrinos behind. The search for answers isn't just philosophical. Experiments like the deep underground neutrino experiment are hunting for traces of neutrino behavior that could reveal their ancient dominance. Tiny deviations in how they oscillate between flavors might carry fingerprints of their primordial reign. And if we're lucky, the next generation of particle colliders could recreate conditions where these particles briefly reclaim their lost power, letting us peek behind the curtain of the universe's first act. What's most humbling is the scale of this idea. The same particles that now slip through your body unnoticed, leaving no trace, might once have been the architects of reality itself. It's a reminder that the universe's history isn't written in stone, but in the faintest whispers of particles we're still learning to hear. What if space-time isn't smooth and continuous like a flowing river, but more like a digital photograph, made up of countless tiny, indivisible pixels? Causal set theory dares to reimagine reality in exactly this way, proposing that the universe isn't built on an endless fabric of space and time, but on discrete, fundamental events that link together like beads on a cosmic string. Forget the infinite density of singularities or the blurry quantum foam here. The cosmos grows not by stretching, but by accumulating these atomic moments, each one a new stitch in the tapestry of existence. At the heart of this idea is a radical simplicity. Space-time emerges from relationships, not substances. Picture a vast, growing network where every event is connected to others in a strict order of cause and effect. You can't have a before without an after, just like you can't build a house by starting with the roof. These causal relationships create a structure so robust that smooth, four-dimensional space-time crystallizes out of it, much like the illusion of motion arises from flipping through the pages of a flipbook. And here's the kicker: because the universe grows by adding new events, there's no need for a Big Bang singularity, just an endless, unfolding genesis where every moment is a fresh creation. This isn't just philosophical elegance, it's a potential solution to some of physics' thorniest problems. Take black holes, for instance. In general relativity, their centers collapse into infinitely dense points where equations break down. But in causal set theory, there's no such thing as infinite density. The inside of a black hole would just be a tangle of events with no single starting point, like a ball of yarn with no end. Similarly, the theory sidesteps the need for dark energy to explain cosmic acceleration. The universe isn't expanding. It's constantly adding new events at the edges, creating the illusion of stretching spacetime. But how does something as concrete as the smooth orbit of planets emerge from this chaotic web? The secret lies in scale. Just as pixels blend into a seamless image when viewed from afar, the granularity of causal sets vanishes at everyday sizes, leaving behind the familiar continuum of relativity. It's only when you zoom into Planck-scale precision, where distances are a trillionth of a meter, that the universe's true, discrete nature reveals itself. Some theorists even speculate that this granularity could leave faint fingerprints in high-energy particle collisions or the blurring of distant gamma-ray bursts, though we've yet to detect them. What's most compelling is how this theory reframes time itself. In a causal set, time isn't a flowing river but a growing tree, with each new event branching from the ones before it. There's no block universe where past, present, and future coexist statically. Instead, The cosmos is an active participant in its own creation, perpetually writing its next chapter. This dynamic view resonates with our intuition that time moves forward, but it also raises profound questions. If the universe grows event by event, could there be a rate at which time unfolds? And if so, what determines it? Causal set theory may lack the flashy dimensions of string theory or the observational triumphs of inflation, but its power lies in its austerity. By stripping reality down to its barest bones, pure causality, it offers a universe that's neither singular nor eternal, but perpetually becoming. And that might be the most revolutionary idea of all, that existence isn't something we're in, but something we're helping to build one moment at a time. What if space and time aren't the bedrock of reality, but something far more elusive, a shimmering mirage emerging from the chaotic dance of quantum particles? That's the radical premise of emergent spacetime, a theory that flips our understanding of the universe inside out. Instead of treating spacetime as the stage on which particles interact, this idea suggests spacetime itself is built from something deeper, the invisible threads of quantum entanglement. Picture a vast cosmic tapestry where every stitch is a connection between particles, and the fabric they weave isn't just metaphor, it's the very structure of reality. At the heart of this revolution is a deceptively simple equation, ER equals EPR, coined by physicist Juan Maldaisner and later refined by Leonard Susskind. This conjecture bridges two seemingly unrelated ideas. On one side, Einstein-Rosen bridges, better known as wormholes, hypothetical tunnels through spacetime linking distant regions. On the other, EPR pairs, named after Einstein, Podolsky, and Rosen, who first highlighted the eerie phenomenon of quantum entanglement, where particles instantaneously influence each other no matter how far apart they are. The equation's audacious claim, these aren't just analogies, they're the same thing. Entanglement creates spacetime, stitching together the universe one quantum connection at a time. Think of it like this. Imagine two people whispering secrets across a crowded room, their words lost in the noise. To an outsider, their communication seems impossible until you realize they're actually holding opposite ends of a taut, invisible string. Every tug is a message, every vibration a shared thought. In the quantum realm, entangled particles are like those people, and the string between them isn't just a connection, it's a tiny wormhole, a warp in the fabric of spacetime itself. Scale this up to countless entangled particles, and suddenly, the smooth geometry of the universe isn't a given. It's a collective illusion, a hologram projected from a network of quantum links. This isn't just theoretical sleight of hand. The math behind ER equals EPR suggests that without entanglement, spacetime would shatter into fragments, like a mirror smashed into a million pieces. Black holes offer a haunting glimpse of this fragility. According to the holographic principle, all the information inside a black hole is encoded on its event horizon, a 2D surface storing 3D reality like a cosmic QR code. But if you cut the entanglement between horizon patches, the interior spacetime dissolves. It's as if the universe has a kill switch, no entanglement, no space. The implications ripple outward. If spacetime is emergent, the Big Bang might not have been the birth of space and time, but the moment quantum entanglement reached a critical density, crystallizing into the continuum we know. Even gravity could be a side effect, not a fundamental force, but the thermodynamic cost of disrupting entanglement, like the tension on a stretched rubber sheet. This would explain why gravity is so weak compared to other forces. It's not a force at all, but a statistical echo of deeper quantum mechanics. Critics argue that emergent spacetime remains a framework in search of definitive proof. Yet experiments are inching closer. Quantum simulators have recreated toy models where entanglement generates geometric structures akin to spacetime. And if the theory holds, it could solve black hole paradoxes, unify gravity with quantum mechanics, and even hint at a universe where here and There, our illusions places only seem separate because we're not entangled enough to see the threads binding them. What's most breathtaking is the humility this idea demands. The solid ground beneath our feet, the vast distances between stars, even the arrow of time, all might be shadows of something far stranger. The universe isn't just in space and time, it's made from them, woven from quantum whispers we're only beginning to hear. And if that's true, then every step you take, every second that passes, is a testament to the most delicate magic of all, the entanglement of everything. Einstein once thought the universe was eternal and unchanging, a perfect cosmic still life where matter quietly replenished itself to maintain balance. This steady-state model, proposed in the early 20th century, imagined a universe without a beginning or end, where new atoms slowly appeared in the voids between galaxies to keep the cosmos looking the same at all times. It was elegant, infinite, and once the Big Bang's explosive evidence piled up, utterly abandoned. But what if Einstein wasn't entirely wrong? What if the steady-state universe wasn't a dead end, but a theory ahead of its time, waiting for modern physics to give it new life? Enter the revamped steady-state model, where the core idea, continuous creation, gets a quantum-era upgrade. Instead of matter magically appearing out of nothing, modern versions propose mechanisms like vacuum energy fluctuations or quantum field distortions, gently coaxing particles into existence. Picture the universe as a self-repairing tapestry. As it stretches from expansion, tiny threads of matter weave themselves into the fabric, maintaining the overall pattern. Some theories even tie this process to dark energy, suggesting that the same force accelerating cosmic expansion might also be quietly knitting new hydrogen atoms into the void. The evidence for this revival comes from surprising corners of cosmology. Certain anomalies in the cosmic microwave background, those faint temperature variations that usually support the Big Bang show patterns a steady-state universe might predict. And then there's the puzzle of impossibly mature galaxies spotted in the early universe, their stars seemingly old beyond time. A steady-state cosmos, free from the constraints of a single explosive origin, could explain these as regions where matter creation has been ongoing for far longer than our timeline allows. But how would continuous creation even work? One daring idea involves the so-called C field for creation, a hypothetical energy field that permeates space, subtly tweaking quantum probabilities to favor particle formation over annihilation. It's like cosmic luck constantly tilting the scales, ensuring that empty space never stays empty for long. Another twist comes from brane cosmology, where our universe's membrane might leak matter from higher dimensions, a slow trickle that looks like creation from our limited perspective. Critics, of course, haven't let go of the Big Bang's mountain of evidence, the redshift of galaxies, the abundance of light elements, the CMB's blackbody spectrum. Yet steady-state supporters counter that inflation, dark energy, and other add-ons have made Big Bang cosmology just as convoluted as the theories it replaced. Maybe, they argue, we're clinging to an explosion because we can't fathom infinity. What's fascinating is how this revival blends old and new. Einstein's cosmological constant, once his greatest blunder, now fuels dark energy research. Similarly, the steady-state idea, once left for dead, lingers as a reminder that the universe might still have tricks up its sleeve. Whether it's right or wrong, it challenges us to ask, are we mistaking a single explosive moment for the whole story, when the truth could be quieter, stranger, and far more patient? After all, if the cosmos is infinite, there's plenty of time for even the most abandoned ideas to find their way home. Supersymmetry paints the universe with a hidden layer of particles, but what if it also sculpted the cosmos through an explosive game of survival? Imagine the newborn universe not as a uniform fireball, but as a seething quantum foam, each bubble a pocket of space-time governed by different physics. In most supersymmetry, the delicate balance between matter and its hypothetical shadow particles shattered almost instantly. but in one rare bubble, ours, it held just long enough for matter to dominate, stars to form, and life to emerge. This isn't just speculation, it's the theory of supersymmetric bubbles where our entire existence might hinge on a cosmic roll of the dice. Picture the first fractions of a second after creation. The universe wasn't yet a smooth expanse, but a chaotic froth of false vacuums, unstable pockets where the Higgs field, the force giving particles mass, hadn't settled into its current state. Each bubble was a lottery ticket with different laws, some where gravity was stronger, others where electromagnetism never existed. Most collapsed almost immediately, their physics too unstable to sustain even basic particles. But in a vanishingly small fraction, conditions aligned for supersymmetry to persist, allowing matter to outlast antimatter and gravity to remain weak enough for galaxies to coalesce. Ours was the lucky bubble, a cosmic jackpot where the fragile symmetry between particles and their superpartners didn't snap under the strain. Why would supersymmetry's survival matter so much? Without it, the universe might have lacked the precise balance needed for complexity. Sussy particles could have stabilized the Higgs field, preventing it from catapulting to catastrophic energies that would have ripped spacetime apart. They might also have provided the dark matter that later sculpted galaxies, or even influenced the strength of the nuclear forces, tweaking the recipe just enough to allow carbon, the backbone of life, to form in stars. It's like a house of cards where every level depends on the one beneath it. Remove Sussy, and the entire structure collapses into cosmic rubble, the eerie implication. Countless other bubbles may have flourished briefly before imploding or giving rise to alien physics universes where black holes dominated instantly or where time flowed backward. Some might still exist, floating beyond our observable horizon like ghostly remnants of roads not taken. And if the multiverse is real, we'll never know how close we came to being one of the doomed bubbles, snuffed out before reality could even take its first breath. Critics argue this is untestable cosmology, a just-so story with no observable evidence, but supporters point to subtle clues: the universe's baffling fine-tuning, the Higgs boson's surprisingly low mass, which Sussy elegantly explains, and even anomalies in particle collisions that could hint at superpartners lurking just beyond our detectors. If future experiments like the high-luminosity LHC spot these elusive particles, it wouldn't just confirm supersymmetry, it might reveal we're the survivors of a cosmic battle royale, the one bubble where the dice landed right. What's most humbling is the scale of the odds. For every bubble like ours, there could be googles of failed attempts, universes stillborn or twisted beyond recognition. It's a reminder that our existence isn't just improbable. It's the result of physics threading an inconceivably narrow needle, where even the slightest shift in symmetry could have erased everything before it began. Whether by luck or some deeper principle we've yet to uncover, our universe wasn't just born, it endured. Darwin's theory of natural selection reshaped biology, but what if the same ruthless competition shaped reality itself? Quantum Darwinism takes evolution's playbook and applies it to the quantum realm, suggesting that the universe we perceive isn't just one possibility among many, but the winner of a silent battle where only the most stable quantum states survive. Picture the early cosmos as a chaotic quantum soup with countless overlapping realities vying for dominance. Most collapsed instantly, too fragile to endure. But a select few, those with the right mathematical resilience, were amplified by their interactions with the environment, eventually crystallizing into the concrete world we recognize. In this view, the chair you're sitting on isn't just solid because of physics, it's solid because it outcompeted every other quantum possibility to earn its place in classical reality. This idea hinges on a peculiar quantum quirk, decoherence. When particles interact with their surroundings, whether photons, air molecules, or even stray cosmic rays, their delicate quantum superpositions crumble, forcing them to choose a single state. Quantum Darwinism argues this isn't random. Certain states are more robust, more likely to withstand these environmental interactions and imprint their information across multiple systems. Think of it like a viral meme. The more a quantum state gets copied and shared by the environment, the more real it becomes. A particle's position, for example, isn't just measured, it's selected, with the universe acting as a relentless editor, favoring configurations that can propagate their influence far and wide. The implications rewrite the rules of observation. In traditional quantum mechanics, the act of measurement feels almost mystical, and observers gaze collapsing waves into particles. But quantum Darwinism strips away the mystique, replacing it with a dynamic where stability equals survival. The reason we all agree on the moon's location isn't because we're observing it, but because its quantum state has been redundantly broadcast through countless interactions with dust, sunlight, and cosmic radiation. It's not that consciousness creates reality, it's that reality is the consensus reached by the environment itself. Critics ask, why do some states win over others? The answer might lie in the mathematics of predictability. States that can encode information efficiently, like a pendulum's predictable swing, are more likely to be replicated than chaotic, ever-shifting superpositions. It's a cosmic version of survival of the fittest, where fitness means being mathematically legible to the universe's encoding system. This could explain why the macroscopic world appears so orderly, even as the quantum realm remains a storm of probabilities. The universe isn't just selecting for stability, it's selecting for communicability, for states that can be reliably shared and decoded by any observer, conscious or not. What's haunting is the scale of rejection this implies. For every quantum state we perceive, uncountable others flickered and died, too fragile to leave a mark. Our entire reality might be the statistical outlier, the one thread in the quantum tapestry that wove itself into permanence through sheer durability. It's a humbling thought. The laws we consider fundamental might just be the ones that outlasted the rest, their rivals erased without a trace. The theory isn't without challenges. Some argue it merely shifts the mystery from observation to environmental interaction, without fully explaining why certain states propagate. Others wonder if it's testable, though experiments monitoring how quantum systems record their states in surrounding particles could offer clues. But whether quantum Darwinism holds or not, it forces us to confront a radical idea. The universe isn't just described by laws, it's shaped by them, forged in a silent competition where only the most resilient patterns get to stay. And that means the world we know isn't the only possible one, just the one that fought the hardest to exist. Gravity wave detectors may not just be listening for cosmic collisions, they could be picking up the faint static of reality itself glitching. The idea of holographic noise suggests that space-time isn't perfectly smooth like a sheet of glass, but pixelated, built from microscopic, indivisible chunks at the Planck scale. Think of it like the graininess in an old film. Zoom in close enough and the illusion of seamless motion breaks apart into flickering frames. Only in this case, the film is the universe, and the grain isn't just visual, it's encoded in the very fabric of existence. LIGO and other gravitational wave observatories are designed to catch ripples in spacetime from cataclysmic events like black hole mergers. But some physicists speculate these ultra-sensitive instruments could also detect something far stranger, the ambient crackle of spacetime's underlying code. Just as your radio picks up static between stations, gravitational wave detectors might sense quantum fluctuations in the structure of reality itself, tiny jitters as spacetime's pixels update their information. These wouldn't follow the clean, predictable waves of colliding black holes, but manifest as an omnipresent background hum, a cosmic white noise whispering the universe's digital origins. This isn't pure speculation. The holographic principle, born from black hole physics, implies that all 3D reality could be a projection from a 2D surface at the universe's edge. If true, then spacetime isn't fundamental, it's emergent, like the surface of a lake emerging from countless water molecules. And just as water reveals its particulate nature through microscopic splashes, spacetime might betray its pixelation through Planck-scale vibrations. Holographic noise would be the artifact of this projection, the cosmic equivalent of a computer screen's flicker as it refreshes its image, the challenge. This noise would be unimaginably faint, buried beneath even the quietest gravitational waves. Detecting it would require instruments thousands of times more sensitive than LIGO or revolutionary new techniques to filter signal from noise. Some researchers propose using future quantum gravity wave detectors, which could leverage entanglement to amplify these subtle effects. Others suggest studying anomalies in existing data, unexplained blips that don't match known astrophysical sources. If holographic noise is real, these outliers might be the first hints of spacetime's pixelated skeleton peeking through. What's at stake isn't just technical, it's philosophical. If gravitational wave static confirms holography, it would mean the universe operates like a vast quantum computer with spacetime as its flickering display. Black holes wouldn't just be cosmic vacuums, they'd be the universe's natural data compressors, squeezing 3D information into 2D bounds. Even our perception of time could be upended, with the arrow of time emerging from the sequential updating of these spacetime pixels, like frames in a cosmic animation. Critics argue that without direct evidence, holographic noise remains speculative, a beautiful idea trapped in the math. But supporters counter that every revolution in physics began as a whisper before it became a shout. Once atoms were hypothetical, now we manipulate them. Black holes were mathematical curiosities, now we photograph their shadows. Holographic noise could be the next great frontier, waiting for the right experiment to tune into reality's hidden frequency. And if we do, the static won't just be noise, it'll be the universe's original language, spoken in Planck-sized syllables since the first moment of time. The question isn't whether spacetime has a code, it's whether we're ready to listen. What if dark energy's mysterious push on the cosmos isn't some exotic force, but the cosmic equivalent of phantom limb pain, a relic from a dimension that no longer exists? The fifth dimension collapse theory dares to imagine exactly that, a universe where our familiar 4 dimensions, 3 of space and 1 of time, were once part of a grander 5-dimensional geometry. Then, in the universe's first moments, that extra dimension crumpled like a deflating balloon, leaving behind a hidden wound in spacetime that now drives galaxies apart at accelerating speeds. Picture a 5-dimensional hypercube where every corner connects in ways our brains can't visualize. In this primordial state, gravity and other forces might have behaved very differently, their influence diluted across extra directions we can no longer access. But as the 5th dimension collapsed, its energy didn't vanish. It got trapped, folded into the fabric of our 4-dimensional world like a crumpled letter stuffed into an envelope. This leftover tension, the theory suggests, could be the source of dark energy's repulsive push. It's not that space itself is expanding, it's that we're still feeling the aftershocks of a dimensional earthquake from the dawn of time. Here's where it gets even stranger. The collapse might explain why dark energy's effects are so subtle yet universal, like a faint hum resonating through all of spacetime. In higher dimensions, gravity could have been stronger, but with the 5th dimension gone, its force leaks into the void, leaving behind the weaker version we know today. Meanwhile, the energy of that lost dimension manifests as dark energy, not a new force, but the ghostly echo of a geometry that once was. Think of it like a piano string snapping. The note it once played is gone, but the vibrations still linger in the air. This idea isn't just mathematical poetry, it's testable. If a 5th dimension existed, its collapse could have left imprints in the cosmic microwave background, subtle temperature variations shaped by the geometry of the rupture. Some models even predict that dark energy's strength should vary slightly over time, a clue that it's not a constant force but a fading relic. Future telescopes like the European Space Agency's Euclid mission could spot these anomalies, catching whispers of a dimension lost to time. Critics argue that extra dimensions remain speculative, with no direct evidence yet. But supporters counter that string theory, brane cosmology, and even some interpretations of quantum gravity all hint at hidden dimensions. We just need the right tools to uncover them. And if they're right, the implications are staggering. Dark energy wouldn't be an awkward add-on to our physics equations, but a cosmic scar, a reminder that reality was once bigger, stranger, and far more intricate than we ever imagined. The universe, it seems, might still be mourning the dimension it left behind. What if the universe isn't just described by mathematics, it is mathematics? Max Tegmark's mathematical universe hypothesis takes this mind-bending idea to its ultimate conclusion. Every structure that can exist mathematically does exist physically. Forget parallel universes with slightly different physics. This is a multiverse where every equation, every geometric shape, every logically consistent system is its own standalone reality. Our cosmos, with its 3 dimensions and specific physical laws, isn't special. It's just one page in an infinite textbook of mathematical possibilities, all equally real. Tegmark's framework, called the ultimate ensemble, strips away the distinction between abstract math and concrete existence. Imagine a vast library where every book isn't just a description of a universe, but the universe itself. One volume details a 4D spacetime where gravity weakens with the cube of distance instead of the square. Another describes a reality built entirely on fractal geometries, where coastlines never end and particles zoom along infinitely jagged paths. Somewhere in that library sits our universe, not because it was selected or designed, but because it's mathematically possible, and in Tegmark's view, that's all it takes for reality to manifest. This isn't just philosophy, it's a testable hypothesis with staggering implications. If every mathematical structure exists, then consciousness itself must emerge from computation wherever complexity allows. A sufficiently intricate fractal could harbor self-aware patterns. A hyperdimensional graph might encode thoughts as naturally as our brains encode memories. Even the concept of physics dissolves into pure math. What we call laws are just the patterns we've observed in our particular equation, while other realities hum to the rhythm of entirely different rules. Critics argue this is radical Platonism run amok, conflating abstract truths with physical existence. But Tegmark counters with a simple question. If math is merely a human invention, why does it describe the universe so unnervingly well? From the Fibonacci sequences in sunflowers to the Higgs boson's mass-matching predictions down to decimal places, math feels less like a tool we created and more like a landscape we're discovering. The mathematical universe hypothesis takes this intuition to its logical extreme. Math isn't describing reality, it is reality, and we're just one of its countless expressions. Yet the theory isn't without paradox. Some mathematical structures are so alien they defy visualization, like infinite dimensional spaces or systems where time loops chaotically. Could these truly be real in any meaningful sense? And how does consciousness, a phenomenon we barely understand, arise from pure abstraction? Tegmark suggests these might not be flaws but clues, hinting that our intuition about reality is hopelessly limited by our evolutionary wiring. What's most humbling is the democracy of this multiverse. Our universe's fine-tuning for life isn't a miracle, it's inevitable because every possible tuning exists somewhere. The constants of nature aren't dialed in by chance or design. They're just the local settings in our corner of mathematical space. Even the concept of nothingness collapses if math requires no physical substrate. Then existence isn't a property to be explained, but a default state. Whether Tegmark's vision holds or not, it forces us to confront the eerie elegance of the cosmos. the universe might not be written in the language of math, it might be the language speaking itself into endless variations. And that raises one final, haunting thought. If every equation is a universe, then somewhere Pythagoras' theorem isn't just true, it's alive. From the explosive chaos of the Big Bang to the silent unraveling of phantom energy, we've journeyed through theories so wild they rewrite reality itself. Imagine entire universes bubbling into existence inside black holes, or cosmic collisions between higher dimensional membranes, ideas that turn our origin story from a simple explosion into an infinite tapestry of possibilities. We've seen space-time pixelated like a digital image, gravity reduced to a cosmic mirage, and even our own existence questioned as a fleeting glitch in a Boltzmann brain's false memory. Each theory isn't just a what if, it's a radical lens that forces us to rethink everything we thought we knew. Consider the elegance of string theory's vibrating filaments, weaving a multiverse where every physical law is just one setting in an endless cosmic menu. Or the audacity of loop quantum gravity, where the universe doesn't begin with a bang but rebounds from a previous collapse like a cosmic phoenix rising from its own ashes. And who could forget the holographic principle, suggesting our 3D reality might be a projection from a 2D boundary we'll never see? These aren't just sci-fi musings, they're the cutting edge of human curiosity, where mathematicians and physicists stare into the void and dare it to blink first. What's truly astonishing is how these ideas intersect. Dark matter, once a placeholder for invisible mass, might have been the universe's first architect. The neutrino, a ghostly afterthought today, could have once ruled a primordial empire. Even time itself might be an illusion, a flickering shadow cast by quantum entanglement's deeper dance. Every theory we've explored doesn't just compete, it collaborates, painting a picture of a cosmos far stranger, far richer than we ever imagined. So now it's your turn. Which of these cosmic origin stories resonates most? Do you side with Penrose's cyclical eons, or does Smolin's black hole Darwinism feel more compelling? Maybe you're partial to the simulation hypothesis, where reality is just code running on some alien supercomputer. Drop your favorites in the comments, debate, defend, and dive deeper. After all, the universe's greatest mystery isn't just how it began, but how many ways we're still discovering to tell that story. And if your brain isn't thoroughly bent yet, don't worry, there's always more mind-blowing science to come. Hit subscribe and let's keep unraveling the cosmos together, one wild theory at a time.